chemistry. So we've talked about some of this stuff. This will tie up some loose ends. So this is radioactivity. This is probably going to be broken up into 2 videos, just so you know. And when you're done with this, you should be able to do homework 7. All right, so nuclear chemistry is the chemistry of the nucleus. So let's review for a moment what's contained in the nucleus of the atom. So I'll hit pause, you hit pause for a second. That's right, so the nucleus of the atom has protons and neutrons. And so remember, the nucleus is positively charged, and all of the mass of the atom is in the nucleus. You might want to review isotopic notation. We can do that. Let me just review that for you quickly on the whiteboard here. So remember, in nuclear notation, in nuclear notation, we have this symbol here, and we have the A number. This is isotopic notation here, and the Z number, where Z is the number of protons, and which is the atomic number, and A is the mass number. Which is the protons plus the neutrons. All right, so we did that stuff before. You might want to review that because we're going to do that again. Let me get back to the slides now. All right, so we're going to go play slideshow. Oops, my bad. Cancel slideshow from current slide. All right. So just as that was a quick review. So remember, the nucleus is held together by what's called the strong force, and the nature of it is not understood. But we know that when we break that, we get a huge amount of energy. Right? That's what nuclear energy is. So just some examples of some isotopes of hydrogen. So remember what isotopes are. Isotopes are the same atom with a different number of neutrons. Also, it's important for this to remember that isotopes have very, very similar properties. Hydrogen's unusual in that it has different names for the isotopes. So protium for just regular hydrogen, deuterium or D, and tritium. And you see they differ just in the number of neutrons. Tritium is radioactive. And some isotopes are just unstable. They just fall apart. So analogous to a sandcastle, or even if you're a homeowner, you know your house is always falling apart a little bit. Everything falls apart. Some of them are more stable than others. Okay? When they fall apart, though, that little grain of sand at the very top is going to fall all the way down here and release all of that potential energy. So what makes it unstable? Too many neutrons, not enough protons. So typically, the ratio of the neutrons to protons for the first 20 atoms, it's about 1. Okay? When you get the heavier atoms, though, when the neutrons to protons ratio is greater than 1, they tend to be unstable. Starting with number 84, which is polonium, okay, everything is radioactive after polonium, starting with polonium. So bismuth is the heaviest atom that has stable isotopes. You look at, this is a graph that has the band of stability, so anything on this side is going to be very unstable. This is the ratio. See here, this is protons and neutrons are the same. So interestingly, when atoms fall apart, they fall apart in well-defined pieces, and those particles are called alpha particles, beta, gamma, and then there's also neutrons. There's also what are called positrons. There's all sorts of different types, but these are the major ones, and we'll go through those. Right? So an alpha particle, so this is the isotopic notation. An alpha particle has 2 protons and 2 neutrons. Okay? A beta particle is basically an electron, so it's written either way, has a -1 effect on the nucleus and a no mass. Remember, electrons don't have any mass. It's kind of the idea that a neutron falls apart and creates a proton and an electron. Gamma radiation doesn't have any nuclear notation because it's not particles, it's just a form of electromagnetic radiation. If you remember the spectrum we went through, it's higher energy than X-rays. So what would be the notation for a neutron? I'll give you a second. Then I'm going to hit a button. That's right, a neutron would be 1, 0, right? Because it has no protons in a neutron. Right. And again, when things fall apart, they follow patterns. So when uranium falls apart, it creates thorium and so on, and then another isotope of uranium. Okay, so you can see how you can turn one element into another element through this type of decay. So I'm going to go through some nuclear equations with you, and that'll take us, I kind of know where I want to stop on this video. So nuclear equations, like balanced chemical equations, mass is conserved. But typically, we're not looking at what the elements are, we're looking at the protons and neutrons. So if you change the atomic number, you change the elements. So if you look at this equation, for example, okay, this is radium, and you see it decays into helium. By the way, let me back up a slide or two here. An alpha particle is basically a helium nucleus, so sometimes instead of writing alpha, we write He. It depends on if the electrons come out. Okay, let's get back to here. So radium decays into an alpha particle or helium, and radon, and you can see how the numbers add up. So 86 plus 2 is 88, 218 plus 4 is 222. So you can see how they add up. So that's what we mean by balanced in terms of nuclear equations. There's a nice lesson on this. I'm pretty sure this still works, so you can check that out if you want to watch a video on it. All right, so I'm going to give you guys a minute to go through these, and then so what would be a good idea would be hit pause, try them, but just as an example, 4 plus what equals 210? 2 plus what equals 84? And then you can use the periodic table to find the element. Let me do the first one for you. All right, so you see 4 plus 206 is 210, right? This is like an equal sign. 2 plus 82 is 84. Then when we say 82, we look at the periodic table and we saw, oh, 82 is lead. So why don't you try the other 4, hit pause on the video, give them a go, and then I'm going to count to 10, and I'm going to go through each one, but you can hit pause in between. All right, so I'm sure you've now come out of your pause. So this one, right, this is a 4, so we need a 1 here. And so that's basically a positron, or it's not even a proton because it doesn't increase the mass, but it's called a positron. Okay, here, 91 minus 1 is 90. Okay, 234 plus 0 is still 234. And element number 90 is thorium. Right here, this is a beta particle. So carbon 14 decays by beta decay. And so what should be here? Negative 1 plus what equals 6? Negative 1 plus 7 equals 6. The top 14 equals 0 plus 14, so this decays into nitrogen. And then this would be nuclear fission. So what's happening here? And again, it's just filling in the blank and doing the math. All right. So 14 plus 1 is 15. If you look on the periodic table, number 15 is phosphorus. 30 plus 1 is 31. So this should be, oops, I'm sorry. 14 plus 1 is 15. 13 plus 2 is 15. Okay. 30 plus 1 is 31. 27 plus 4 is 31. And a 4, 2 is helium. All right. So make sure you can do those. There's some on the homework. Again, these are just types of radioactive decay, and also remember when these things come out, they don't just fall out. They come out at very high energy. All right, so again, we're not going to worry about the mass, but the penetrating power here, right, what can stop it? So for example, alpha, beta, and gamma, the two major parts. Okay, alpha particles are pretty big, and they can't even get through your skin. Beta particles can get through your skin, but they can't get through, like, you know, the pieces of aluminum. And gamma can get into you really bad, right? Interestingly, that's the ion, but the ionizing power is inversely related to the penetrating power. So bigger particles have more trouble getting through, but if they do more damage. So it's a big particle. Remember, ionizing is, you know, being able to knock electrons off, break chemical bonds, things like that. So alpha particles are the most dangerous in terms of ionizing, but they can't get into you. But let's say if you were to ingest something that gave off alpha particles, like drank something, ate something, then it would already be in, right? So we talked about ionizing radiation before in terms of the ultraviolet. Okay, and so what it can do is it can do damage to tissue because it knocks electrons off of things or it can break chemical bonds. and it can affect cells, especially those that are rapidly dividing, because rapidly dividing cells are doing a lot of protein synthesis and DNA synthesis and things like that, and so there's a lot more chemical reactions going on. Okay? And again, ionizing radiation, cosmic rays, gamma rays, X-rays, alpha, beta, gamma are all ionizing radiation. So the effects, well, again, it can cause, think of it like sunburn. Okay? Sunburn is from ultraviolet, that's ionizing radiation. So radiation would be like sunburn, but just a lot worse because it's more ionizing than UV. If you back up, remember ultraviolet is before X-rays, right? There's ultraviolet, X-rays, gamma rays, and cosmic rays. So, and these things would be kind of after X-rays as well. So ionizing radiation is going to depend on the energy and how close you are to the source. Radiation sickness is kind of like just a huge, really, really bad sunburn. But again, it's the same idea that skin is going to peel. And again, it could peel on the inside, so to speak, right? So that's why radioactivity can be very, very damaging because it does the same thing that sunburn does, but it's just much, much worse. So, in sunburn, your skin peels. Well, imagine if it was on the inside of you, what it could do. Background radiation is the amount of radioactivity that's already around, existing in the background. So it's just there in the environment. There's nothing you can do about it. Okay. So radon, for example, naturally occurring gas. Uranium is in the ground. Some building materials will have smaller parts. So in a spoonful of, say, charcoal or the lead in your pencil, there's going to be some radioactive carbon. It just naturally occurs. Again, when you put a lot of it together, it's just like heat. If I have a small amount if I have heat spread out over a large surface versus if I focus it. Think about maybe when you were a kid or you knew someone who took a magnifying glass from the sun and like burned ants or burned holes in paper. It's the same idea. If I take a lot of that energy, I put it in one place, it's much more damaging than if it's spread out. So this is just naturally occurring. Okay, man-made radiation left over from testing from nuclear weapons, nuclear power plants, medical diagnostic tests, X-rays and things like that. Okay, luminous watch dials. I'll tell you a story about that in just a moment. Okay, and these are just units of radiation. Okay, I'm going to stop on this slide. Let me back up and tell you a little story about luminous dials. A buddy of mine, when I was in graduate school, had a lot of cancer in his family, so he didn't work with any radioactivity. And when you work with radioactivity, you'll typically be monitored. So people who work in radiology wear film badges because X-rays expose film. And once a month, they submit their film badge to the environmental health and safety group at where they work, and it gets exposed, and they say, oh, this person is okay, or they've been exposed to too much radioactivity. And if that's the case, then they have to take a break from it. So when you're working with radioactivity, you'll be tested every so often. So my colleague Pete wasn't working with radioactivity. And when environmental health and safety came into our lab to check everybody out, we were all sitting over in the clean area eating lunch, and he would always test our coffee cups and our backpacks and things. And so he tests Pete's backpack, and the thing goes off scale, the Geiger counter. And Pete nearly choked on his sandwich. And he hadn't been working with any radioactivity. And so when he opened up his bag, he had this watch his grandfather had given him. And the watch had a radium dial. It was that old. And so I think it's in a display case at this point. Just in another example, it was noticed that people who worked in these factories had a high incidence of cancers. And again, radium doesn't really give off that much. You'd have to ingest it. But so they were watching, and they had women that were painting the dials by hand with a radium-based paint, and they would lick the paint, the tip of the brush, to make a small tip. And they were drinking the paint over long periods of time, so they changed the process. All right, so I'm going to pick up on this slide at the next video.